Software errors are prevalent. It's easy to make them, and it's hard to find them. In this lecture, we'll explore topics related to the finding and removal of bugs within our C++ programs, including learning how to use the integrated debugger that is part of our IDE. Although debugging tools and techniques aren't part of the C++ standard, learning to find and remove bugs in the programs you write is an extremely important part of being a successful programmer. Therefore, we'll spend a bit of time covering such topics, so that as the programs you write become more complex, your ability to diagnose and remedy issues advances at a similar pace. Programming can be challenging, and C++ is somewhat of a quirky language. Put those two together, and there are a lot of ways to make mistakes. Errors generally fall into one of two categories: syntax errors, and semantic errors, logic errors. A syntax error occurs when you write a statement that is not valid according to the grammar of the C++ language. This includes errors such as missing semicolons, using undeclared variables, mismatched parentheses or braces, etc. For example, the following program contains quite a few syntax errors. #include int main std_could hi there, x, invalid operator. Return 0 missing semicolon at end of statement. Fortunately, the compiler will generally catch syntax errors and generate warnings or errors, so you easily identify and fix the problem. Then it's just a matter of compiling again until you get rid of all the errors. Once your program is compiling correctly, getting it to actually produce the result you want can be tricky. A semantic error occurs when a statement is syntactically valid, but does not do what the programmer intended. Sometimes these will cause your program to crash, such as in the case of division by 0. #include int main int a equals 10 int b equals 0 std_could a b equals ab. Division by 0 is undefined. Return 0 #include int main int x std_could x. Use of uninitialized variable leads to undefined result. Return 0 #include int main. Return 0, function returns here std_could hello world, so this never executes. Modern compilers have been getting better at detecting certain types of common semantic errors, e.g. use of an uninitialized variable. However, in most cases, the compiler will not be able to catch most of these types of problems, because the compiler is designed to enforce grammar, not intent. In the above example, the errors are fairly easy to spot. But in most non-trivial programs, semantic errors are not easy to find by eyeballing the code. This is where debugging techniques can come in handy. Let's say you've written a program, and it's not working correctly. The code all compiles fine, but when you run it, you're getting an incorrect result. You must have a semantic error somewhere. How can you find it? If you've been following best practices by writing a little bit of code and then testing it, you may have a good idea where your error is. Or you may have no clue at all. All bugs stem from a simple premise: something that you thought was correct, isn't. Actually figuring out where that error is can be challenging. In this lesson, we'll outline the general process of debugging a program. Once a problem has been identified, debugging the problem generally consists of 5 steps. Find the root cause of the problem, usually the line of code that's not working. Ensure you understand why the issue is occurring. Determine how you'll fix the issue. Repair the issue causing the problem. Retest to ensure the problem has been fixed and no new problems have emerged. When debugging a program, in most cases the vast majority of your time will be spent trying to find where the error actually is. Once the issue is found, the remaining steps, fixing the issue and validating that the issue was fixed, are often trivial in comparison. Let's say you've noticed a problem, and you want to track the cause of that specific problem down. In many cases, especially in smaller programs, we can quickly home in on the proximity of where the issue is. Int main. Get names, ask user to enter a bunch of names. Sort names, sort them in alphabetical order. Print names, print the sorted list of names. Return 0. If you expected this program to print the names in alphabetical order, but it printed them in opposite order instead, the problem is probably in the sort names function. In cases where you can narrow the problem down to a specific function, you may be able to spot the issue just by looking at the code. First, there's a lot more code to look at. Looking at every line of code in a program that is thousands of lines long can take a really long time, not to mention it's incredibly boring. Second, the code itself tends to be more complex, with more possible places for things to go wrong. Third, the code's behavior may not give you many clues as to where things are going wrong. If you wrote a program to output stock recommendations and it actually output nothing at all, you probably wouldn't have much of a lead on where to start looking for the problem. Finally, bugs can be caused by making bad assumptions. It's almost impossible to visually spot a bug caused by a bad assumption, because you're likely to make the same bad assumption when inspecting the code, and not notice the error. So if we have an issue that we can't find via code inspection, how do we find it? Fortunately, if we can't find an issue via code inspection, there is another avenue we can take. We can watch the behavior of the program as it runs, and try to diagnose the issue from that. This approach can be generalized as: figure out how to reproduce the problem. Run the program and gather information to narrow down where the problem is. Repeat the prior step until you find the problem. The first and most important step in finding a problem is to be able to reproduce the problem. The reason is simple: it's extremely hard to find an issue unless you can observe it occurring. Back to our ice dispenser analogy, let's say one day your friend tells you that your ice dispenser isn't working. You go to look at it, and it works fine. How would you diagnose the problem? It would be very difficult. However, if you could actually see the issue of the ice dispenser not working, then you could start to diagnose why it wasn't working much more effectively. If a software issue is blatant, e.g. the program crashes in the same place every time you run it, then reproducing the problem can be trivial. However, sometimes reproducing an issue can be a lot more difficult. The problem may only occur on certain computers, or in particular circumstances, e.g. when the user enters certain input. In such cases, generating a set of reproduction steps can be helpful. Reproduction steps are a list of clear and precise steps that can be followed to cause an issue to recur with a high level of predictability. The goal is to be able to cause the issue to reoccur as much as possible, so we can run our program over and look for clues to determine what's causing the problem. If the issue can be reproduced 100% of the time, that's ideal, but less than 100% reproducibility can be okay. An issue that occurs only 50% of the time simply means it'll take twice as long to diagnose the issue, as half the time the program won't exhibit the problem and thus not contribute any useful diagnostic information. Let's start with an easy one. If your program is exhibiting erroneous behavior, one way to reduce the amount of code you have to search through is to comment some code out and see if the issue persists. If the issue remains, the commented out code wasn't responsible. Int main. Get names, ask user to enter a bunch of names. Do maintenance, do some random stuff. Sort names, sort them in alphabetical order. Print names, print the sorted list of names. Return 0. Another problem common in more complex programs is that the program is calling a function too many or too few times, including not at all. In such cases, it can be helpful to place statements at the top of your functions to print the function's name. That way, when the program runs, you can see which functions are getting called. With some types of bugs, the program may be calculating or passing the wrong value. We can also output the value of variables, including parameters, or expressions to ensure that they are correct.